Alexander Markov. Yes, I think I do. He does black hole mass estimates. And yeah.
Basically the M sigma and this.
Yes.
So he's the PI of Andy's instrument, this high resolution spectrography ELT. So he was here last week in the seminar. So that time, 2 times it was disconnected, the seminar, because
so I should get ready.
So we hope that this time with you it will be
okay. So if it gets disconnected, I just have to like basically log back in, right?
Yes.
Yeah. Okay. Yeah, thanks. So that's I'll be prepared. So what is how many AGN astronomers do you have in Aries?
So apart from me, this Alok Gupta is working mostly on AGN, and Amitesh works on Galaxy a little bit, but not on AGN.
Yeah.
Galaxy. Hello. So.
Yeah, no, I was thinking more in terms of students. I think I do know all the AGN astronomers.
Yeah, some students, Alok Gupta, I think he has 3-4 PhD students.
Okay.
Pankaj was here and he's still visiting, but Pankaj.
Yeah.
So he joined Aizan Mohali as a faculty.
Okay, very nice. Okay.
And probably Jitesh is also working, so he is in the list.
Yeah, so you have a good group, actually. You can actually have an AGN discussion.
Yeah, sure.
Very nice.
So we can start now.
Okay.
Good afternoon, everyone. So today, as a part of our weekly seminar, we have Professor Preeti Kharb. She obtained her BSc from Miranda House College, which is under DU, Delhi University. And then she did her master MSc in physics, MSc from DU itself in 1996. Then she joined JNU in 1997 for her pre-PhD work, and then followed that for PhD from IIA in astrophysics in 2005. Just after completing her PhD, she did several years of postdoc. First, it was in Rochester Institute of Technology, and then Purdue University in the US. Since in 2012, so she joined as a faculty at IIA Indian Institute of Astrophysics, Bengaluru as a reader in 2012, and recently in 2016 she moved to NCRA, where she has been working as an associate professor. So she is mostly interested in AGN and an expert in jet physics in AGN. So we'll hear from her more about her research and the ongoing activities. So welcome, Preeti. You could start your presentation.
Thank you, Subhendu. Thank you first for inviting me, and I'm really excited to do this talk. And I hope to interact afterwards with the students and anybody who's interested. Okay, so let me make this full screen. Okay. So this looks fine, and yeah.
Yes.
Okay. All right. So hello, everyone. Today I'm going to talk about the radio loud, radio quiet AGN divide, which has been the focus of our studies for a couple of years now, and how we've been using multi-scale radio observations to kind of, probe this question. So let me start with this slide, which is kind of a nice lead-in to the talk today. And so on the top, of course, is this very exciting result that came last month of the Event Horizon Telescope image of the central black hole in our own galaxy, which is a very modest supermassive black hole with a mass of, a million solar masses. And our Milky Way galaxy is, in every sense, a very typical spiral galaxy. So to image the supermassive black hole in a typical spiral galaxy is a revelation. And especially if you combine this with the other exciting result, which actually happened almost a decade ago, which was when the Fermi Gamma Ray Telescope looked at the Milky Way galaxy. It discovered what are known as the Fermi Bubbles, which are shown here, which are very symmetrically placed above and below the galactic disk, as you can see here. And also, if you followed the Event Horizon Telescope results for the Milky Way, you know that the data and the modeling suggests that this black hole accretion disk system is nearly face on. The inclination is around 30 degrees, which is actually a little bit not in keeping with this very symmetrical Fermi bubbles above and below the galactic disk. So and there have been suggestions actually for many, many decades now that there was kind of a low luminosity AGN active galactic nucleus in the Milky Way. And at some point, jets from this black hole may have produced the Fermi bubbles. So with this slide, I will start my talk, because I think the conclusions that we draw from our study kind of also become relevant in this in the light of the Milky Way results. So let me start by the standard introduction to the first class of active galactic nuclei, which were discovered by Carl Seifert in the 1940s. And so again, this is a typical spiral galaxy face on, which seems to show an increase in the stellar density as you move to the center, as opposed to another galaxy, which is also a face on spiral, but seems to have a star-like nucleus superimposed on the center. And which you can see from this, the diffraction pattern here, which suggests it's a point source. And this point source can be so luminous that it can outshine the light of the entire galaxy by a factor of 100 even. So this is an active galactic nucleus. The second interesting feature of this active galactic nucleus, which we later, of course, learned more about. At that point, these were just peculiar spiral galaxies with a star-like nucleus. And the second intriguing thing about these galaxies was the optical spectrum. So in a normal galaxy, the spectrum is like this, which is dominated by absorption lines, which actually are from the photospheres of the stars that make this galaxy. But the spectra of an active galactic nucleus is dominated by emission lines, as you can see here. And there are so-called narrow lines, as well as lines which are stand on broad bases, which are known as broad lines. So much later, this type of galaxy then, of course, came to be known as a Seifert galaxy. And it was found that Seifert galaxies showed a variety of spectra, but primarily of two kinds. So this was, that's where the classification of type 1 and type 2 came about, where type 1s were the ones which seemed to have lines showing broad bases, like here, whereas type 2 were the ones which didn't show these broad bases. So even much later in the 1980s, it was also recognized that there were some other kind of AGN, which were dominated by emission lines, but the low luminosity lines, for example, O2, as you can see here on the top, there is a Seifert 2 spectrum, and at the bottom, there is a liner spectrum, that all the low ionization lines like O2 or S2 become prominent. So these are the low ionization nuclear emission line regions or liners. So in my talk today, I'm going to speak about both Seiferts and liners together. I will not be distinguishing between these. And of course, this after a lot of studies of the spectra of these active galactic nuclei, a picture of the central engine has been kind of drawn out in this figure, which you are, I'm sure, very, very familiar. But at the center of everything is a supermassive black hole, which has a mass of 1 million to 1 billion solar masses. Matter is accreting onto it, most probably in an accretion disk, as you see here in this pink feature. And all the spectra, the broad lines that were seen in the spectra come from fast-moving dense clouds around this black hole accretion disk system. The narrow lines seem to come from less dense and slower moving clouds further away, called the narrow line region. The widths of broad and narrow lines are broad are several thousands of kilometers per second, and the narrow ones are several hundreds of kilometers per second. We also know the density of these clouds which produce these lines based on the spectra itself, and the line ratios versus the presence and absence of certain lines has given us a range of densities in the clouds which emit these lines. Also, we suspect that there is some obscuring torus-like structure. We don't know if it's exactly a torus or some kind of a warped disk, which seems to hide this black hole accretion disk system and the broadline region with certain lines of sight, so that when it's completely blocked, you only see the narrow line clouds and you see a spectrum of type 2. When it's not blocked and the AGN is oriented in such a way that you can see the broadline region and the accretion disk, then you have a type 1. Now, somewhere in this vicinity of this black hole accretion disk system, outflows are launched, as you can see here, the yellow things, bipolar outflows. And here is now an actual image of a very famous active galactic nucleus called Cygnus A. This is just the radio frequency image of that, where you can see what we saw in the cartoon. You have the central engine. Here we call this the radio core, and you have collimated outflows of jets and lobes and hotspots, etc. Now, it's very clear based on two main properties that this radio emission is coming from incoherent synchrotron emission. And incoherent synchrotron emission basically occurs when you have charged particles moving at relativistic speeds around magnetic field lines, as shown in this cartoon. One of the main characteristics of synchrotron emission is high linear polarization, and these, the maximum of which is around 70–75%, and that is always consistent with the observations. We find it's all the radio emission is highly polarized, but never more than 75%. And the second defining feature of this emission is that it has a power law spectrum, a power law continuum spectrum, as you can see in this slide. So if you just plot the flux density with respect to frequency, you have this kind of a slope, and which always has a spectrum, a slope of around 0.7, 0.75. So these two features, because of these two properties, we know that the radio emission is synchrotron emission, which is being emitted by the bipolar outflows. What is not clear is how these jets are launched. So jet formation in AGN is an open question. And here, this figure is, this is of course a cartoon, as you can see, which shows magnetic field lines, maybe strong poloidal magnetic field lines are kind of threading the accretion disk in the black hole. And due to the rotation of the system, the magnetic field lines then get kind of twisted, and this forms a conduit or a passage or a way to collimate an outflow. So one of the most popular mechanisms which have been proposed to produce a jet came from Blanford and Znayak, where both the energy and angular momentum of this rotating black hole is used to power the jet. And if the magnetic field strength, for example, of the system was B and the angular velocity of this black hole system was omega, then the power that can be extracted is B square omega square. So it's you can extract, the faster the spinning black hole, the more the power in the outflow. Another mechanism which has been proposed for outflows is the Blanford and Payne. There are several others as well. There are hybrid models as well. Where in the Blanford and Payne, the energy and angular momentum are extracted magnetocentrifugally from the accretion disk rather than the black hole. Okay, so now I'll come to the main topic of today's talk, which is the radio loud, radio quiet AGN divide. So this figure is to show you what these two classes are in pictures. And on the left, you see a radio optical overlay of a galaxy. So you have a bluish looking elliptical galaxy in here. It's not bluish, but in this picture, this structure that you see here is an elliptical galaxy. And the red emission that you see is radio emission coming from the AGN in this galaxy. And what's interesting, what is important here is that these outflows can span hundreds of kiloparsec and megaparsecs in scales, going way beyond the host galaxy itself. And this is just the high resolution image of the same. But on the right, what you see is a spiral galaxy, which is seen here in green. You can see the spiral arms, and red emission being X-ray emission from hot gas in this galaxy. And the pink blue emission that you see is the radio outflow. It's also bipolar, just like we had in the cartoon, except now that the outflow is very small, and it doesn't typically exceed or doesn't typically go beyond the confines of the host galaxy. So it's usually several tens of parsecs, hundreds of parsec in extent, and up to a few kiloparsec or 10 kiloparsec in extent. So this is the radio loud radio quiet divide, that there is a small fraction of AGN with very large jets and a large fraction of AGN with small jets. So this divide was quantified in this work by Kellerman in the 1980s, where they looked at this sample called the Palomar Bright Quasar Survey. And when they plotted this ratio of flux densities in the radio to the optical, they found, which is plotted here for the sample, they found a bimodality. So in the R values, that most of the sources seem to have R less than 10, which was then termed as radio quiet AGN, and only around 10-15% of the quasars in their sample had R values greater than 10. And so these are the radio loud objects. So radio loud, radio quiet, and that this kind of divide definition has stuck around, though more recently there is a lot of debate if such a bimodality actually exists, and is R equal to 10, for example, a good number to make this demarcation. So there are many, radio loud radio quiet divide has been a topic of great interest in the community, and many suggestions have been put forth to explain what produces radio loud versus radio quiet AGN. So the initial suggestions centered around the differences in black hole masses and black hole spins, which were both expected to be larger for the radio loud sources. More recently, and I can talk more about this if anybody's interested, I think these are not that much in favor, because especially black hole spins, where they have been measured for a lot of Seyfert galaxies, which seem to then show very fast spinning black holes. Another suggested difference has been differences in accretion rates. And I think this is kind of now a very popular model to explain the radio loud, radio quiet divide. There is also suggestions, and in fact, we do know that a lot of the radio loud AGN reside in elliptical galaxies, whereas radio quiet AGN reside in spiral or lenticular galaxies. And so differences in environment are supposed to be important, and jet medium interaction could also be one of the reasons, or it could be a contributing factor in producing radio loud versus radio quiet AGN. Another suggestion, which has been around for a long time, is that in this paper actually dealt with Seyfert galaxies, but in general, radio quiet AGN, maybe the AGN activity is short-lived, and as suggested by Sanders and others. And in the entire lifetime of this radio quiet AGN or Seyfert galaxy, which could be as large as 10 to the 8 years or around, there are several episodes of activity. Each of them just lasts around 10 to the 4 to 10 to the 5 years. So that is the reason why, that's one way to explain why the Seyfert jets are not very long. So this is another suggestion, that they just don't last long enough to, make large jets. So now I've divided my talk in these 4 parts: episodic activity, magnetic field structure, parsec scale structure, and a composite radio loud, radio quiet source. And these are four pieces of work that we've carried out with our group. And I will try to show how these all, try to answer the question of the radio loud versus radio quiet. So first is episodic activity. So it's kind of been clear looking at just the images of some Seyfert galaxies that activity in them must have been episodic. And one of the best examples is this Seyfert galaxy called Markarian 6. So here you see 3 panels, which are basically radio emission shown in grayscale at 3 different resolutions. So what is seen in this first image is bubble-like lobes, H-shaped lobes, which are in total extent is around 15 kiloparsec. Even though they're large, they're still within the confine of the elliptical galaxy, lenticular galaxy that these reside in. The center is very bright, and when you look at the center with higher resolution data, then you find that another set of 8 shaped lobes are seen in a different direction compared to the larger lobes. And an even higher resolution image with the Merlin telescope, for example, shows that the inner structure seems to be an S-shaped jet. So there seems to be 3 episodes already in this galaxy. It's difficult to explain all of these different structures in different directions from one episode of activity. So already with these, you can see that if you assume that the jet speed is around 0.1 times the speed of light, which is often done for assumed and also obtained in a couple of Seyfert galaxies, which were looked at with multi-epoch, very long baseline interferometric observations, that 0.1 C may be a good number for the velocities. And with just those velocities and these extents, you can see already that the source each activity episode has been around 10 to the 4, 10 to the 5 years. And we actually, in our 2006 paper, model these 8-shaped structures with precessing jets. And also because you can see that clearly much better in this central thing, like it seems to be like a jet which is precessing. And those time scales were also of these order 10 to the 5, 10 to the 6 years. So in terms of morphology and modeling, you can see that this AGN is episodic. Another good example is NGC 2639. This is work that was part of our PhD student Binnie Sebastian's thesis, where she noted this Seyfert galaxy also seemed to have at least 3 activity episodes based on the outflows being in 3 different directions and 3 different scales. So, so this is the north-south lobe, which is much smaller in extent compared to Markarian 6. This is only 1.5 kiloparsec in extent. And the center actually had this east-west extension in a different direction. And then that center looked at with very long baseline interferometry seemed to show a jet which is not exactly aligned with the east-west outflow. Binnie also had observed these sources with polarization, and these red ticks that you see are polarization electric vectors. So these lobes were highly polarized, which means, of course, that they are synchrotron emission. And the extent of these, as I mentioned, are small. So 1.5 kiloparsec. This is only 360 parsec, and this is a 3 parsec long jet. So we only had kind of 2 frequency data. So we obtained the spectral index of these different features. And so we could not do a very sophisticated spectral aging analysis, which is actually what is needed to kind of get some sort of ages of these outflows. But we did like a first order calculation using this relation. So this is a relation to obtain electron lifetimes given the equipartition magnetic field in that structure and a break frequency where the spectrum kind of changes its slope. And this break frequency, of course, we could not obtain because we had 2 frequency images, but we assumed it to be around 1.5 gigahertz, which is what is actually also typical for sources which have multi-frequency data. It seems to show a break frequency around there. And these B values are equipartition magnetic fields and the magnetic field equivalent to the CMB radiation, redshift, and so through this relation, we could obtain the lifetimes of these different lobes. The equipartition estimates are given here, for example. And this relation, actually, I should specify, only assumes 2 ways of losing energy for the electrons. One is through the synchrotron radiative losses and the inverse Compton losses over CMB photons. So just these 2 ways of losing energy will then give you a electron lifetime. And for this north-south lobes, we estimated the electron lifetime to be around 16 million years, and the east-west lobes were around less than 1 million year. So these are the numbers. I think I would not take them very seriously. I think we were trying to get a rough estimate of the lifetimes of these sources, but many assumptions go into this. But what is very interesting is that more recently, we have now looked at the source with the GMRT, And so now let me show these images here. So this north-south lobe, which Binny had worked on in her thesis, is shown here. And this is the the SDSS image of this galaxy. You can see a dust lane. The extent of this source is also clear. And at the bottom is a digitized sky survey image in the color. And the red contours are the 650 megahertz radio emission, which shows a much larger outflow in a completely different direction. It's a few kiloparsec in extent. All this inner structure is already inside the core here. So this shows not only 3 but at least 4 episodes based on our data. So I think just on the basis of these, definitely episodic activity does take place in CFIC galaxies. The second piece of work deals with polarization. So this is again now starting with the Markarian 6 image. So this is again the Markarian 6 image in contours with the ticks now showing polarized emission, polarization electric vectors. So for all this emission, which is assumed to be optically thin, which it is, even if you took the spectral index, you find that this is optically thin. It's a steep spectrum. The magnetic fields are inferred to be perpendicular to the electric vectors. So you basically find that the magnetic field lines are aligned with the lobes here in both the cases, or both the lobes. And this seems to be a very common phenomenon in several CFIC galaxies that we've looked at. So this is also from Vinny Sebastian's thesis work. This is a galaxy NGC 4388. And here, this radio emission, these radio contours here are actually emission from the host galaxy, the galactic disk of this galaxy. And the north-south emission here is from the AGN. So these are the lobes, and they're highly polarized. And again, these are electric vectors. So polarization is aligned with the edge of the, rather B fields are aligned with the edges of the lobes. And in this particular source, we also found another set of polarization vectors, which suggests the B fields are poloidal in the center. This is also seen in this source, NGC 5506. This is a little more kind of oriented closer to our line of sight. So you have to imagine, so this is the bipolar outflow, but closer to our line of sight. So here again, the E vectors here suggest that the B fields are aligned with the edges. And in the center, again, you seem to have a poloidal magnetic field structure. So this kind of polarization work has not been extensively done for at least a large sample of CFIC galaxies. They have been carried out for individual galaxies. So these are some of the papers that have dealt with polarization images of CFIC outflows. And so Binny gathered all these data and found that as many as 40% of the sources seem to show this kind of poloidal B field structure in the center. But most of them, 70%, show this B field aligned with the edges. So this seems to be a very common structure in the CFIC lobes. And this becomes important when I show you the final piece of work, which is on the composite source. Coming to the third part, which is the parsec scale structures. So this is probed by very long baseline interferometry. So VLBI is basically carried out when you have radio telescopes which are widely separated and not, for example, connected by cables or optical fibers. And the only constraint you have for these, how far these telescopes can be, is that they should be sampling the same wavefront from the radio source, or a quasar in this case. So, so these baselines can be arbitrarily large, as large as the diameter of the Earth. And so here you basically record all the radio data on magnetic tapes, and then you accurately timestamp them with the most accurate clocks that we have, which is hydrogen maser. And later you play the tapes back and correlate the data. Because you can have these very arbitrarily large baselines, you can have this arbitrarily large resolution, because that is a ratio of the wavelength to the diameter. So in this case, the baseline. And VLBI typically results in resolutions of milliarc seconds. And for these sources, which we are looking at, these are not very high redshift sources. Milliarc second usually corresponds to spatial scales of a few parsecs. So before I show the results of the VLBI observations of CFERTs, I wanted to refresh your memory with the, the standard relations that come into play when you go look at VLBI images, because you're now dealing with the jet as it's just launched from the accretion disk black hole system. It is highly relativistic. And so the relations that come into play are from the special theory of relativity. And some of these results are even counterintuitive. So here, this R parameter here is basically the intensity ratios of the jet versus the counterjet, which is given by this relation, where beta is the speed of the jet with respect to speed of light, theta is the orientation of the jet. And so typically when you look at VLBI images of most of these AGN, they show these one-sided jets, as you can see from this example, which is basically saying that the jet which is approaching you is brighter than what it is in the jet frame, and the jet which is going away from you becomes dimmer than it is in the jet frame. And so artificially you see this kind of a structure, which is dependent on the jet speed and the orientation. The second important relation to remember is that the speeds with which jet components move, which is the beta apparent, or speeds respect to speed of light, the apparent motion of jet components is given by this relation. And because of this relation, sometimes this beta apparent can even be greater than 1, which then gives rise to superluminal motion, or motion of jet components greater than the speed of light, which is of course just an optical illusion. So with these, let me just show you the results of these VLBI observations. So the sample that we started with is a small sample, only 9 CFERT galaxies and liners. And the parent sample is called KISS-R, KPNO Internal Spectroscopic Red Survey. It's an optically selected survey and basically has optical spectra through SDSS, as shown here. We selected these galaxies as being interesting because their lines that you can see, prominent lines, also seem to have double peaks. So these kind of double peak lines have been suggested in the literature to either come from binary black hole systems, where you have 2 black holes with 2 narrow line regions, or it could be that the narrow line region itself is very disk-like. So you have the approaching side and the receding side, which is blue shifted, red shifted. Or you could have something as simple as the jet NLR interaction, where the jet is pushing the narrow line clouds away from you or towards you, and then they give rise to these double peaks. The second selection criteria was that these sources had to already have been detected in some kind of radio survey. So the Very Large Array first survey, we use that survey to see if they already had detections, because this is a prerequisite for carrying out VLBI observations. Because if there is no first detection, then it's very likely that we'll not detect anything in VLBI. So, this study actually gave some very interesting and surprising results. So on the top is again a radio optical overlay of one of these CFERT galaxies. So you see this spiral galaxy clearly. The green contours are the VLA first radio contours. The total flux density of this is only 4 millijanskis. So what I want to emphasize here, it's actually a very, very weak radio source. And it's a point source. But when you look at this with VLBI, you see a nice long jet, which is almost 150 parsec in extent. It's curved. And this few color pixels here is because we also had another frequency data which only detected the inner part of the jet. And all this emission is steep spectrum, which is also a little bit surprising, because usually the base of the jets are synchrotron self-absorbed and usually have a flat spectrum, but this is all steep spectrum. And other interesting thing was that it's like a core jet looking structure, but only one-sided. There is nothing on the counterjet side. So it seems to be one-sided, which is usually a signature of relativistic jets, which is not expected in CFERT galaxies. CFERT galaxy jets are expected to be slower. Of course, because just from these observations, all we could do was kind of get some constraints on the jet speed, assuming that this one-sidedness was because of Doppler boosting effects, using the relation that I showed you in the previous slide. if we assume that we don't know any of these numbers. So if you assume that the orientation of this jet is greater than 50 degrees, which is consistent with the fact that this is a Seyfert type 2 galaxy, and that the torus half opening angle of Seyfert galaxies and other AGN have been suggested to be around 50 degrees. So we assume that theta should be 50 degrees or more. And if you do that, then you can, from the jet to counterjet brightness ratio, you can get an estimate of the jet speed, which in this case turns out to be 0.75 C. It's very large. Not as large as what you see in blazars, but very large, larger than what you expect in Seyfert galaxies. Similarly, many other sources which looked very boring. This is another one of those target sources, again, another point source, very weak, 2.5 millijanskis. When you look at them with VLBI, they seem to show some kind of a core jet structure, even here. The extents of these jets are several tens of parsecs. The incidence of the jets in the sources that we looked at is more than 60% had these jets. And following the method I just talked about in the previous slide, this jet speeds may range, of course, these are just limits, may range from 0.003 C to 0.75 C. Whether this is actually Doppler boosting or free absorption is not clear at this point. But it would be very interesting if these jets turn out to be truly relativistic. So we have just recently obtained second epoch data for these observations, and we are hoping to see if there is actual jet motion like suggested here. So hopefully there'll be more results. So let me then now also add the information that we have from the emission lines themselves, because we chose them on the basis of these double peak lines. We could do these kind of modeling. This is basically a line ratio figure, and the grid here comes from a certain model. In this particular case, the modeling code is called mappings 3, and it's a plasma modeling code. And the model that is shown here is called the shock plus precursor model. So there we use several different models to see where the data lies. And so the data, for example, fits very well for most of the sources with this shock plus precursor model. So in the shock plus precursor model, you basically have some kind of a shock producing outflow, and the post-shock gas is actually the source of photoionization rather than, so AGN photoionization didn't work as a model for these sources, but shock plus precursor model seems to work for most of the sources. So we concluded that it looks like in this sample, at least, since we also see jets, it looks like the double peak lines are mostly due to jet medium interaction. But what was interesting was that the line peak separations don't indicate very large speeds. The line peak separations, that the double peak lines that we saw in the SDSS, suggest differences of only a few 100 kilometers per second. This, of course, is a much smaller value than the speeds of the jets, which can be 10 to 100 times higher. So one way to explain this is, so we are saying jets are moving the gas, but it looks like it's not the jet head which is pushing away the gas, but maybe gas is being pushed in the lateral direction. So that could explain, the results for the velocities and our conclusion that this is jet medium interaction. Or the other model is that the emission line gas itself is flowing in some kind of a wider outflow. So this is shown here as a cartoon. And so this cartoon, of course, has been in the literature. This is not our work. Several authors have actually explained these double peak lines as coming from this nested biconical outflows, which actually fits with our picture of what's happening in these galaxies. So you may have a jet plus wind scenario, which is ongoing in these sources. So could it be that you have a combination of both the Blanford's-Naik mechanism for the central part of the, the outflow, and the Blanford Payne mechanism for the outer part of the outflow? It could be. We don't know. Let me now come to the last part of the talk and the last set of results.
If I may ask, so all the 9 sources that you have selected for that, they are all type 2 AGNs? Or?
Yes, all type 2
AGNs.
Yeah.
So, and what is the typical line width of this combined line profile? in the H alpha, or let's
The
say
line widths are also just a few 100 kilometers per second.
Yeah. Okay, so 100. Okay, and any of the objects has a kind of optical light curve or any variations in the optical light curve?
No, good question. I don't think they have. So
Okay.
these sources are not very well studied also. I mean, the sample itself is, I don't think they have.
So,
So they're definitely worth pursuing with,
Okay, please go.
So this is just the last part. Now I'll try to kind of add all those results in this one particular source study that we did. This is NGC 2329, which is a powerful wide-angle tail radio galaxy, which you can see here, this very large galaxy, which, large outflow, almost 130 kiloparsec in extent, which is actually the center of the Able 569 galaxy cluster. This is the central galaxy in that cluster. And what is interesting is that the center of this, the so-called core of this outflow, in higher resolution images shows a structure like this, which is very similar in morphology as well as extent. The extent is only around 10 kiloparsec to what you see in a Cepheid galaxy. So this is what intrigued us initially, and we thought, so that's interesting. It's almost like the center kind of, the core kind of looks like a restarted AGN, and it seems to have a Cepheid-like outflow rather than a FR1 or Fanner-Rayleigh type 1 radio galaxy outflow. In terms of the spectral index, the outer lobe seemed to be on average steeper. They had an alpha of average alpha of -1, and the core itself, which is the structure, had a slightly flatter spectral index. Again, this is usually an indication of restarted activity in an AGN, and so we again, just using those simple relations of electron lifetimes, we estimated the ages of these two outflows, and they turn out to be 40 million years for the large outflow and 25 million years for the small outflow. Again, not to be taken very seriously, the numbers themselves. What was interesting was that this source had also been observed in polarized light, and this is old observations from 85 of these two outflows, the larger one and the smaller one. So here again, these ticks are polarization vectors. And what you can see immediately here, of course, for all this optically thin emission, the B field is perpendicular to the electric vector. So I show it here. So you can see here immediately that this wide angle tail outflow seems to show what is known as a spine sheath B field structure. So you have this inner spine, which seems to have B fields perpendicular to the outflow, and the sheath structure, which has B fields aligned at the edges. So this kind of structure has been observed in several Fanner-Rayleigh type 1 radio galaxies, as Eric Perlman's work, etc., and have been suggested to be due to jet-medium interaction, as for example, Robert Lang's work. The inner outflow, the smaller core itself, that was not very nicely imaged. So in our 2021 paper, we used some archival VLA data, which was not published. And people have, I don't know, it wasn't looked at in polarized light for some reason. And so now these are the polarization images from those data. So I will not focus on it's basically consistent with what was already seen earlier. And this is now the inner part, much more clearly you can see now. Here I've already rotated the electric vectors by 90 degrees. So now what you see is the B field. And you see this bubble-shaped kind of B field structure with aligned B fields. And this is what we saw also in several Cepheid galaxies. So it was very interesting that not only in morphology, but also magnetic field structures seem to resemble FR1 for the outer lobe and a Cepheid-like for the inner lobe. So that was very curious. Second thing that was curious was that when you look at the source's radio loudness parameter, which is actually, so plotted, this red thing is plotted here. And this figure itself comes from this famous work of Shikora et al., where these authors plotted the radio loudness parameter with respect to the Eddington ratio, which is basically the ratio of the volumetric luminosity to the Eddington luminosity. It's some kind of an indicator of accretion rate. And these different types are basically so what these authors, which was actually a very famous finding, which has been discussed a lot, is these two what are they called? I mean, basically you have two streams here, right? Two different sets. So on the top is the radio loud set and the bottom is the radio quiet set. So you have Phanerophyte type 1 radio galaxies, you have broadline radio galaxies, you have radio loud quasars on the top. And then on the bottom, you have Cepheid galaxies, liners, and radio quiet quasars. So these two, and then, so this is the radio loud, radio quiet jump that you see, which these authors tried to explain by differences in black hole spins. So our source here, this composite source, falls exactly in the middle of everything. It has a radio loudness parameter of a few hundred and not thousands, which is what is normally seen in very powerful radio sources. So we suggested that, so I think the first thing, important thing here to remember is that if this is true, I mean, if these two episodes are one like a radio loud AGN, one like a radio quiet AGN, the first thing to remember is that the black hole mass cannot be important. And black hole spin could be, but I think black hole spin has also fallen out of favor due to many other reasons. So the best thing that could explain this source is if the accretion rate somehow changed between two episodes, and maybe it was a low accretion state initially, which then, because accretion rate also decides the structure of the accretion disk. When you had the low accretion rate, you had what is known as an ADAF disk, which is advection dominated accretion flow. And this kind of a disk then gave rise to a strong jet, which gave rise to the FR1 episode, the larger episode. At some point, the AGN switched off and restarted with a higher accretion rate. At this higher accretion rate, the disk became a combination of an ADAF and a standard disk. A standard disk is the famous optically thick, physically thin disk, which was put forward by Shakura and Sunyaev in 1973. And this kind of a jet then disk gave rise to a weak jet, giving rise to the Cepheid episode. So now I will just, that was the last slide of my thing. So now I try to put all these things together to see what we have found. So it looks like the activity, AGN activity in Cepheid galaxies and liners is short-lived. The polarization observations seem to show some characteristic beacon structures on kiloparsec scales. And interestingly, the 10 to 100 parsec scale jets that are observed in Cepheid galaxies are one-sided, which could be consistent with Doppler boosting, but also other effects. So it's possible that the short-lived activity is the primary reason, not the only reason, but the primary reason for outflows being stunted in radio quiet AGN. I put a question mark here. Of course, this needs to be tested, of course. And somehow accretion rate and therefore the accretion disk state is all important, so that radio loudness is actually a function of the epoch when it's measured. As I think this is kind of consistent with the last source that I discussed. And this idea has actually gained a lot of currency recently by all these papers presented here, where these authors have suddenly found a source which was radio quiet to become in time scales of years. It's turned out to be suddenly become a radio loud source. So I will stop here and again leave this image, which kind of the Milky Way, I think, which kind of also ties up with this idea of the talk. So thank you, and I'm happy to take questions.
Thank you, Preeti, for this wonderful talk and giving us a tour to this AGN, radio loud and radio quiet. So now we have time for question and answer. So please raise your hand or put your question in the chat box. Shivangi, please go ahead.
Hello, ma'am. Very interesting talk. So I wanted to ask this question. The episodic activity that you talked about. So does different kinds of AGN also, we have observed in different kinds of AGN also episodic activity?
Yes. Yes. So, for example, about the double radio galaxies, etc. Right? So even the X-shaped sources. I mean, there are several other kinds of AGN, which also show episodic activity. I think the difference may be in the, though we're not sure, I mean, maybe one of the differences may be the time scales on which the AGN is active versus when it's not. I think that may be different. And at least for the double radio galaxies, somehow the jet direction doesn't change between episodes, which we don't seem to find in most of the Seaford galaxies. There, the jet direction is also different. So, but it's been known. Episodic activity has been known in several different classes of AGN.
Okay, and my next question is, do we know that why some AGNs have one-sided jet and others have two-sided?
Okay, so actually, all AGN have two-sided jets. That's the first thing. They just appear to have one-sided jets because of these Doppler boosting effects. So that's the main thing. So in the frame of the AGN itself, you always have a two-sided outflow.
Okay, thank you, ma'am.
Yeah.
Any further questions from anyone? There are many students, so please, you guys should ask questions more and more. So, okay. Anyway, so before they ask anything, so I just go ahead with some questions.
Yes.
So, so is there anyone compared this double peaked NLR emissions for radio detected and radio undetected sources? Radio detected and radio undetected, because I think this Brazilian group, what is the name of this lady? She actually worked on this double peaked NLR with this nice velocity, maps. So I mean, because all the sources you showed that they are all radio kind of quiet. So I mean, I was wondering what would be the difference between similar kind of source but radio silent completely.
Yeah. So actually, it'll be nice if you point out which work this is, because we kind of biased our sample selection itself to choose only sources which had radio detection. So we kind of didn't even look at the sources which didn't have radio detection. So, but are we talking about which group is this?
It's Teresa. I forgot the name.
Taisa? But Taisa doesn't do. Does she do double peak AGN? I haven't. Okay.
NLR emissions, they do biconical outflows, and they explain with these biconical outflows.
Right. Oh, right. So just interaction of the jet with the.
Yes.
Yeah, that's a yeah. So I don't know if anybody has done a systematic search of double peak lines at radio frequencies. Maybe I'm forgetting. I don't know. I can't remember, because I think most of these studies are usually done either in the the emission lines or in the radio. It's almost very difficult to find both these. So I can't remember right now. And so I think what is interesting is that even though these are all radio quiet, they all seem to have jets, and these are small jets, but they all have jets almost. Yeah. So I haven't really found a totally radio silent source. I'm not convinced that they exist.
Yeah. So so you showed some images where you have the host galaxy contours, radio emissions, and then AGN contour was there.
Yes.
So what is the separation? I forget. I mean, what is the spatial scale for?
Okay.
Those?
Okay. So for example, here.
Yeah.
Like, okay. So the first, so this image is around. I think this is around 5 arcsecond resolution, and the scales are around almost 5-6 kiloparsecs.
Okay.
Yeah.
Okay.
So this is just the central.
So you exclude that these emissions are not from host galaxy at all? They
could be. Some of this emission could be from the host galaxy also. But with the VLBA, of course, we just detect the AGN part of it. But it's possible that there is some contribution also coming. But this doesn't show very well. They're almost like point sources.
Okay.
But I think galactic contribution cannot be ruled out. Yeah, must be there. But it's already very weak. The source itself is very weak. So maybe I can ask you a question, Suvendu, just in case the other students have not. Are students familiar with radio observations? And because I don't know if I went too fast and didn't explain.
No, I mean, less. I think very less people are doing observations itself. Some of them are, I think, taking the data from this integrated flux data already from archive. So,
Right. Yeah.
And this you showed one diagram where these bubbles like structure created by the magnetic field it's this nice circular. So, and what was the reason that you said that it could be
this one?
This one, yes.
Yeah. So the reason I don't know, but it seems to resemble what we saw in the CIFR galaxies. Not so well. I mean, usually they were at the edges, but this is this kind of some edge. There seems to be the B field is kind of it's almost like a bubble which is somehow compressing B fields at the edges. So that kind of structure seems to be commonly seen in CIFR galaxies. And so the point I was trying to make was that this inner so-called core seems to have not just the morphology of a CIFR galaxy, it also seems to have a magnetic field structure like a CIFR galaxy. It's almost like the source restarted and was like radio quiet AGN rather than a radio loud AGN.
And this there's a plot where you pointed this radio loudness and Eddington ratio, this one plot. So how this Eddington luminosity was calculated for these particular sources, because they are all type 2 and you need a mass to calculate, I guess.
Oh, I see. No. Okay. So this particular, this is all this is data from the literature from Shikura's paper, and our target is only this source, which is this particular source. So it's not even a type 2.
Okay.
This composite source.
Okay.
So this composite source also has a radio loudness parameter, which is intermediate. So not only does it have like a FR1 Seifert kind of thing, it also has a radio loudness parameter, which is like intermediate.
Okay, and so Eddington ratio, how did you calculate that from?
So Eddington ratio, I think we did basically bolometric by. So I think that's the standard way. It's estimated, right? Like 5,000 angstrom.
So what? Yeah, so that bolometric is coming from 5,000 angstrom, but Eddington luminosity is coming from black hole mass itself.
From the black hole mass, yes. So this galaxy has a black hole mass estimate.
Okay, I see.
It's a very kind of well-known galaxy, galaxy cluster.
Okay.
Yeah, it's a famous galaxy.
Yeah, I just wanted to know that if it is from the emission line FWHM or any other.
Oh, I see. I don't know where this particular black hole mass came from. That I don't remember, but I think it may have multiple estimates of black hole mass in this particular source.
Okay, so is there any further questions from our audience?
Hello, ma'am.
Yes.
Ma'am, in the same slide, when you were mentioning the radio loudness parameter, so you said that black hole mass estimation is not dependent on this parameter. So how is that?
No, black hole mass is definitely needed here. But this particular source, I don't know where, if it's come from the M sigma relation or something, more serious was actually done to estimate black hole mass in this particular source. But this is a value from the literature. So this galaxy is kind of well studied in the literature. But the black hole mass is definitely important. How it was estimated, I don't remember. Did that answer your question?
Yeah, yes.
Okay.
I think he was going to ask something else. He was saying that, I think you mentioned one time that the black hole mass, this plot shows the black.
Okay, good. Okay, yes, that's an excellent point. So what I was trying to say was that when people in the literature say that differences in black hole masses are responsible for radio loud versus radio quiet sources, we are saying that you see both kind of episodes in this particular radio galaxy. So obviously black hole mass cannot be important. It's the same source. It's restarted. So maybe once upon a time it was radio loud, now it's radio quiet. So it can't be the black hole mass, right? So only thing that could have been different is that maybe between these two episodes, the black hole spin somehow changed. But then black hole spins are already not in favor. They've fallen out of favor because of these results where people actually tried to estimate spins, which is from these iron K alpha lines. And those were estimated for a lot of radio quiet AGN. And they were actually very high. The spin parameters are close to 1 for radio quiet AGN as well. So spin also cannot be important. So the only other way we can explain this is that there was somehow between episodes a change in the accretion rate, and then that change in the accretion rate then gave rise to a different kind of accretion disk in the second episode. And so that could explain, I think that could explain all these results together.
So you are considering that between two epoch of episodes, the black hole mass is constant.
Yes.
Okay, but what is the separation between these two epochs?
That's a good question. So I mean, again, the separation, like I said, I don't know how seriously to take these two numbers, but the electron lifetimes for the outer lobe was around 40 million years, and the inner is like half of that. So
okay, I see. So because I was just wondering, because if you want to grow a black hole to a large mass, then it has to grow through a lot of episodes and merger.
But I think that will not be significant enough, for example, to change. I mean, the black hole mass, I don't remember how much it was in this particular source, but it's most likely around 10 to the 8, 10 to the 9 solar masses. So I think in 20 million years, how much you can, change the mass of the black hole is the question. I don't think that can be changed significantly between episodes. Black hole mass must be definitely growing between these episodes, but has it grown that much is the question. It's only 10 to the 7 years. I mean, usually black hole masses should happen over 10 to the 9 years, no?
Yeah, if you consider it interlimited accretion.
Yeah. So I think you're right that black hole mass should have been growing between these episodes, but I don't think it's significant enough.
Okay. So if there are no further questions, let's thank Preeti again, and we hope that you'll be able to visit us sometime in the near future.
Thank you. Thank you, Subhendu. Thank you, Shivangi, for asking questions. I'm very happy to, if anybody has any questions, to answer by email, etc. Thank you.
I'll let you know. Okay.
Okay, thanks. Bye, Subhendu.
Thanks all the participants for attending, and we'll meet again another time.
Yes.
So bye-bye.
Bye.
Bye.